Hello, I'd like to thank everyone for coming to our press conference. We think we have a lot of exciting news to tell everyone. This conference is going to be in English, but you can ask questions afterward in German, and we will have the material available in German as well. I'm going to give you a background on the company, and then my colleague Lutz Darling is going to give you the information on our latest study for these high-efficiency vehicles. The Scuderi Group really started in 2002. It was a family organization. Back then, we started with very few people, and we had an idea on how to improve the performance of internal combustion engines. That was our split cycle concept. It has grown since that point to where we now have almost 500 patents in over 50 countries. We have offices now in the United States, Frankfurt, Germany, and Nagoya, Japan. Our technology team has grown tremendously as well. It includes companies like Southwest Research Institute out of San Antonio, Texas, as well as Bosch Engineering out of Albstadt, Germany. The technology itself is really the key to our company. It breaks down into really three major components. The basic concept is what we call our split cycle engine. It's where we've separated the intake and compression stroke from the power and exhaust stroke. And this side of the engine really represents the intake and compression. This compressed air flows through a crossover passage where the air under high pressure is fed into our power cylinder, and combustion occurs as the power cylinder is in the downward motion. It's what we call firing after top dead center. This system enables the other systems, which are our air hybrid and our Miller concept. The air hybrid is where we have basically taken an air storage tank and connected it to our crossover passage. That enables the engine to actually recapture and reuse energy like an electric hybrid, except we do it using compressed air. We have found that it's much simpler. It's actually able to capture energy and reuse it more effectively. Costs are much, much lower, and it's actually more reliable because there's nothing there to wear out. One of the bigger features of our engine, though, recently that we've developed is what we're calling the Scuderi Miller cycle. And that is where we're able to take and use a conventional turbocharger and pick up energy off the exhaust, have it actually do some of the compression work of the engine, which then allows us to downsize the compression side of the engine and reduce the amount of compression work coming off the crankshaft. What that does for us, it actually has more of the work coming out of combustion ending up on the crankshaft. Some very significant results of the combination of these three features. First of all, the engine actually is producing much higher output, much more efficiency, and you'll see that in the study that we've done recently that Lutz will talk about. We're producing less emissions, less CO2 emissions. Our torque level is very high. In fact, our gasoline engine will rival the torque of just about any diesel engine on the market, but it does this while maintaining very low pressures inside the engine, so the wear and tear on the engine is actually very low. So there's many exciting features about this engine, and what we did is we did a study recently comparing the high-efficiency vehicles as they currently are against these vehicles with our engine in it. And I'm going to now hand this over to my colleague Lutz, which he'll discuss the high-economy vehicle project with
you. Thank you very much, Sal. Yeah, what we did actually is, especially for the IAA show here in Germany, a study of highly efficient vehicles with our engine in there. Means all that Sal explained, all the technology we have developed over the years, we have put that into that study. And it's basically a group of 10 vehicles which are seen as the most efficient vehicles here in Europe, starting with the Fiat 500, for example, the twin-air engine, Hyundai i10, there is the Daihatsu Cuore is in there, up to the Toyota Aygo. All of those vehicles are considered to be very, very efficient. And to take a look at that graph, what we did is we did an average vehicle, or we actually did a study or did a median from all those vehicles. And we have some figures here that are average to that group. Means the capacity, for example, is 1.03 liters. The power of the group here is 74 horsepower. The economy is means 4.47 liters per 100 kilometers, and the CO2 emissions are 104. Transmission is manual. The weight of the group, the average is 927 kilograms, and the drag or CW-wert is 0.33. And what we did now is to actually build our own vehicle model. That means we wanted to match the weight of that vehicle. It's a little more here, it's 950 kilograms. The drag is the same, 5 gears engine. And our engine model is a Scuderi split cycle engine with 74 horsepower. And the acceleration is from 1 to 100 kilometers in 13.5 seconds. And when we did that study, we came to that results. The conventional engine or conventional vehicle here had an engine, the size was again 1.03 liter or 1030 cc. The power was 74 horsepower. Fuel consumption on that vehicle was 4.5 liters per 100 kilometers or 53.5 miles per gallon. And the CO2 emissions were 104 grams per kilometer. When we put a Scuderi engine in here without, again, changing anything else, our engine had a size of 880 cc. That means it's quite smaller. It has more power, 77 horsepower. And the fuel consumption actually is 3.7 liters per 100 kilometers or 65.4 miles per gallon. And the CO2 emissions here are only 85 grams per kilometer. And with this, we would already meet, I think, 2020 CO2 levels. And this is only with a conservative analysis that we did. As Sal mentioned, we have Southwest Research Institute, who are a well-known lab in the United States. Also, they also work for European companies. And they did this study for us, actually. For example, with a very low turbo efficiency and other things. So there is a lot of potential still in there. It's already approximately 20% reduction in fuel consumption and CO2 emissions. But we internally think we will get much more out of that. So maybe to sum that up, also our engine, based on all that study we did here, is based on our prototype, which is running since June 2009 and shows very, very good data compared to Otto or diesel cycles. We are in board-level negotiations now with several companies, both in the automotive industry as well as in the power generation, heavy truck industry. The German, European, and as well US government is informed about that technology and shows a lot of support. If you take a look at that of the engine design we have compared to the Otto cycle or the diesel engine, our cost structure and the supply chain remains intact. It means we are not more expensive than a conventional engine, and the OEM can use their supply chain. It means our engine consists more or less of 97–98% parts that are also being used in the Otto engine or diesel engine. Our engine is not limited to cars. It could be used in ships, trains, generators, everywhere where you could see a Otto engine or a larger diesel engine, for example. And it's not fuel specific. It means it can run on natural gas, it can run on biodiesel, it can run on hydrogen if wanted, it can run on diesel and fuel. We think we have a technology here which is a great solution to reduce the global CO2 footprint right now, because our engine technology, still we are developing it further, but still already it has reached a level of efficiency and CO2 reduction which is better than the existing engine technology out there. We think as soon as and our business model is not to sell this engine, not to produce it, we are actually licensing our technology, and that means as soon as we have the first licensing agreement, and that's what the OEMs told us, this technology will be on the market within the next 2 to 3 years. And this is the end of the presentation. Thank you very much again for for coming here, and we are happy to answer your questions now, also in German if you like. Thank you.